Good morning, my dear students. Today I am going to continue with the lesson of capacitors and dielectric. This is the second video that I am going to present. In this video, we shall be discussing about capacitors, principle of capacitors, and their combination. So, first thing we will discuss is a capacitor. What is a capacitor? As we know that capacitance of a conductor can be increased by increasing the size of the conductor, placing the conductor in a medium of large dielectric constant, bringing other conductors near to it. So capacitance of a conductor can be increased by these methods. Now what is capacitor? Capacitor is such an arrangement in which the capacitance of a conductor is increased by bringing another earth conductor near to it. We are talking about a parallel plate capacitor. A capacitor essentially consists of two conducting plates near to each other. One of these plates is earthed or connected to the earth. Now we'll discuss principle of capacitor. In the capacitor arrangement, the increase in the capacitance of a conductor is due to the decrease in potential V. Charge remains constant. When another conductor is brought near to it. So let us consider an arrangement. We have a metallic plate A which is positively charged. Another neutral plate B is brought near to it. What happens? Since A is positively charged, it has got positive charge on both inner and outer surface. B has got no charge present over it. When B is brought near A, then a negative charge is induced on the surface or inner surface of B. The potential of the system A and B remains the same because the potential due to positive and negative charge on B cancels out. This is to be understood. Potential remains the same. Then what we do? We connect the metallic plate, the outer surface of the metallic plate, to the earth. Now, when we talk about the metallic plate B, what has happened? When the charges were developed on the inner surface, negative charge was developed on the inner surface of metallic plate B. As a result, all the positive charge was on the outer surface of metallic plate B. Now we have connected the metallic plate to the earth. As a result, the positive charge on the outer surface of the metallic plate B gets neutralized and B is left only with negative charge. Now this results in the decrease of the net potential of the system due to the sum of positive potential on A and negative potential on B. The potential gets decreased. Earlier it was more. Now since the B plate has got negative potential present over it, the potential of the system decreases. To increase the potential to the same value as was initial in the beginning, an additional amount of charge has to be given to plate A. What are we doing? We are again giving extra amount of charge to the plate A. This means that we are increasing the capacity of storing charges on A. We are giving extra amount to bring it back to the same potential V. Now this has increased the capacitance of the arrangement or the ability to hold more amount of charge. The system so formed is called a capacitor. So capacitance of a capacitor. If the charges on the plate of capacitor are plus Q and minus Q, and the potential difference between these plates is V, then the capacitance is given by the formula C equal to Q upon V. So the capacitance of a capacitor is defined as the ratio of the charge given to the plate of the capacitor to the potential difference between the plate. C is equal to Q upon V. The net charge on the capacitor is always 0. The capacitance of a capacitor does not depend on charge Q and on the potential difference V. Each conductor is like a capacitor whose other plate is at infinity. Okay, I hope you have understood what is capacitance of a capacitor. Now we'll have an expression for the capacitance of a parallel plate capacitor. A parallel plate capacitor consists of two long plain metallic plates mounted on two insulated stands and placed at a smaller distance d apart. The plates are exactly parallel to each other, and the space between these two plates is filled with air or some dielectric material. So we have an arrangement here, two plates that are placed at a distance d apart. Each plate has got surface charge density sigma, that is equal to Q upon A. Plate A has got a charge sigma. Sigma is surface charge density. We find out the potential difference. There is an electric field that is developed on the plate between the two plates. First plate is positively charged, the other plate is negative charged. So there is an electric field that is going out from the positive to the negative charge, represented by the letter E. So potential difference between the plate is given by the formula V is equal to ED. V is equal to ED. So we put the values here. V equal to E upon D. The electric field due to the intensity of electric field due to a metallic plate is given by the formula E equal to sigma upon epsilon naught. So potential difference is equal to sigma upon epsilon naught into D. Or we substitute the value of surface charge density, then V is equal to QD upon A epsilon naught. We have substituted here the value of electric field intensity, that is sigma upon epsilon naught. So what are we getting? We are getting V is equal to QD upon A epsilon naught. Q upon A is equal to sigma, surface charge density. Now we know that capacitance is the ratio of the charge to the potential. So C is equal to Q upon V. We get the formula for the capacitance of a parallel plate capacitor. C is equal to A epsilon naught upon D. Okay. So the formula for the capacitance of a parallel plate capacitor is A epsilon naught D. If the space between the parallel plate is filled with dielectric medium or relative permittivity ER, then C is equal to A epsilon naught epsilon R upon D. Or if it is filled with the dielectric material of dielectric constant K, then C is equal to K epsilon naught A upon D. Then capacitance of a parallel plate capacitor is directly proportional to the area of plates. From the formula, C is directly proportional to A or C is inversely proportional to D, the distance between the plate. Next we have dependence of the capacitance of a capacitor. The capacitance of a capacitor depends upon the following factors. First, on the area of the plates. So, the capacitor is directly proportional to the area of the plate. How can we see this? We have a parallel plate capacitor, two metallic plates A and B that are of equal size. So, we have A and B, two metallic plates. B is connected to the earth and A to a gold leaf electroscope. On giving some positive charge to the plate A, the leaves of the electroscope diverge. Now, if the plate B is moved up or down from the present position so that the overlapping area of the plate is reduced, the divergence of the leaves increases. This means that on reducing the area of the plate, the potential difference between the plate increases. The capacitance of the capacitor decreases. So, the capacitance of a capacitor depends upon the area of the plate and is directly proportional to it. The second factor on which the capacitance of the capacitor depends is the distance between the plate. If the plates A and B of a capacitor are kept at a definite distance apart and positive charge is given to A, then the leaves of the electroscope diverge. Now, if the distance between the plate is reduced, the divergence of the leaves decreases. This means that on reducing the distance between the plates of the capacitor, the potential difference between the plate decreases. The capacitance of the capacitor increases. Otherwise also, from the formula, V is equal to ED. So, potential is directly proportional to D. And we have capacitance is equal to Q upon V. So, it becomes C is equal to Q upon D. So, capacitance is inversely proportional to D. Then third factor on which the capacitance depends is the medium between the plate. So, the capacitance of a capacitor depends upon the medium between the two plates and increases for a dielectric medium. It is proportional to the dielectric constant K. So, if in between the metallic plates of the parallel plate capacitor we fill a dielectric material of dielectric constant K, then the capacitance of that capacitor increases by K. It is a very important factor. If the space between two metallic plate, if the space between the two metallic plate is filled by dielectric material K, then the capacitance of the capacitor increases to K times. Capacitance of a parallel plate capacitor with dielectric slab between plates. Let us consider a parallel plate capacitor having plate charge Q, plate area A, and plate separation D. Suppose a slab of some dielectric material of dielectric constant K and thickness T, which is smaller than D, is introduced between the plates. The molecules in the slabs get polarized and there is an internal electric field EP developed in the dielectric slab, whose direction is opposite to the external electric field as shown in the diagram. EP is the electric field that is developed inside the dielectric medium material, and E naught is the external electric field, that is the electric field between the plates of the capacitor. Then the net electric field inside the capacitor, inside the dielectric, is En, which is equal to E naught minus Ep. Okay. If sigma be the surface charge density on the plates, then the electric field in the air between the plate is given by E naught equal to sigma upon epsilon naught, which is equal to Q upon epsilon naught A. Then we know that the net electric field will be equal to E naught upon K. Okay. Net electric field En is equal to E naught upon K. So the potential difference between the plates of the capacitors VV, which is equal to EV, we know that V is equal to ED, so we multiply this. In the free space, the electric field is E naught, and the area of the distance between the free plates without the dielectric is D minus T. So V is equal to E naught D minus T. And within the dielectric, the potential difference EPT, that is EP into T. T is the thickness. So the net potential is equal to E naught D minus T plus E naught upon K into T. On solving, we get V is equal to E naught in common, in bracket D minus T plus T upon K. Then charge is equal to E naught into epsilon naught A. So E naught is equal to sigma upon epsilon naught, which is equal to QA upon epsilon naught. We know that capacitance is equal to Q upon V. On substituting the values, we get the capacitance is equal to A epsilon naught upon D minus T plus T upon K. This is the formula for a capacitor which has got a dielectric medium placed between the plates of the capacitor. Okay, that is C is equal to epsilon naught A upon D minus T plus T upon K. Is it clear? Then we have special cases. Since dielectric constant K is greater than 1, the effective distance between the plates become less than D, and so the capacitance increases. If you look in the expression, C is equal to epsilon naught A D minus T plus T upon K. Now D minus T, the value will be less than D, and T divided by K, which is greater than 1, will have a smaller value. So the denominators decrease, the capacitance increases. So once we place a dielectric material between the plates of the capacitor, the capacitance increases. Now there are certain special cases. If the dielectric slab fills the entire space between the plates, complete distance D is filled with the dielectric material, that is T equal to D. Now we put the value of T equal to D, then D minus T is 0. And then the formula becomes D upon K, that is C is equal to K epsilon naught A upon D. Okay, the formula becomes K epsilon naught A upon D. Now if you remember this, we had the formula of parallel plate capacitor in the last part, that was equal to C is equal to epsilon naught A upon D farad. Now if the empty space between the plate of capacitor is filled with dielectric constant K, then the capacitance increases to K times. So it becomes K times epsilon naught A upon D. If there be vacuum in the whole space between the plate, that is T equal to 0, there is no dielectric material. In this above expression, if we put T equal to 0 and K equal to 1, we get the formula C naught equal to epsilon naught A upon D. If there be a slab of material K equal to infinity of thickness T plates between the plates, then the capacitance will be C is equal to epsilon naught A upon D minus T. Okay, if the dielectric material of infinite constant placed between the parallel plate capacitor, then the C is equal to C is equal to epsilon naught A upon D minus T. Combinations of capacitors. In many situations, we need to combine two or more capacitors. There are two main methods of combination of capacitors. Capacitors can be either combined in series or in parallel. So first we will discuss the series combination. In this series combination of capacitor, the first plate of the first capacitor is joined to the electric source. The second plate is joined to the first plate of the second capacitor. The second plate of the second capacitor is joined to the first plate of the third capacitor, and so on. And the last plate is connected to the negative plate of the source. Okay. So as you can see in the diagram, we have the first plate of the first capacitor C1 is connected to the positive terminal of the battery. So it requires positive charge. As a result, there is a negative equal and opposite negative charge develops on the second plate of the capacitor C1. Now this second plate is connected to the first plate of the capacitor C2, and so on. So negative to positive, they are all in series combination. Okay. Now the important thing about this combination, as you can see that Q charge develops on the capacitor positive plate Q. The same charge is developed on each plate of the capacitor. The positive plate has got plus Q charge, the negative plate has got minus Q charge of each and every capacitor that is connected in the series combination. So the charge remains the same in each capacitor. The potential V of the source is divided across each capacitor. Across the capacitor C1, potential is V1. Across the capacitor C2, potential is V2. Across the capacitor C3, potential is V3. The sum of all these individual potentials V1, V2, V3 is equal to the net potential difference applied across the arrangement. Okay. So V equal to V1 plus V2 plus V3. V equal to Q upon C, that is the potential, total charge upon total capacitance. So V equal to Q upon C, where C is equivalent capacitance, Q is the net charge. We substitute these values, V equal to Q upon C, V1 equal to Q upon C1, V2 equal to Q upon C2, and V3 equal to Q upon C3. So we substitute this value in the equation V equal to V1 plus V2 plus V3, we get Q upon C equal to Q upon C1 plus Q upon C2 plus Q upon C3. So charges on both the sides cancels out. The equivalent capacitance is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. That is, the reciprocal of the effective capacitance is the sum of the reciprocal of the individual capacitance. That is, the effective capacitance in series combination is smaller than the least capacitance, the smallest capacitor's capacitance. Is it clear? Like for example, if we have two capacitors of 2 microfarad and 3 microfarad, they are connected in parallel in series. So the equivalent capacitance will be equal to 1 upon 2 plus 1 upon 3, that is equal to 5 upon 6 equal to 1 upon 1.2 farad. So effective capacitance will be equal to 1.2 farad or microfarad. Then in that case, the effective capacitance is smaller than the smallest capacitor that is used. The smaller capacitor that we had used was of 2 microfarad. Then the effective capacitance has come out to be equal to 6 upon 5 or 1.2 microfarad. That is the meaning, that the effective capacitance is smaller than the least capacitance that has been used in the combination. The second type of combination is a parallel combination. In this type of combination, the first plate of all the capacitors are connected to one point and the second plate to the another point. So there are three capacitors C1, C2, C3. They are connected in parallel between the points A and B. The point B is connected to the negative terminal of the source, and point A, the first point, is connected, all the positive plates are connected to the positive terminal of the plate V. Okay. Suppose plus Q charge is given to the point A by the source B. The charge is distributed on all the plates 3 capacitor according to their capacitance. By induction, equal amount of negative charges are induced on the inner surface of second plate of the capacitor. So the charge distributed on each capacitors are different. They are Q1, Q2, Q3. And the potential across each capacitor is the same, V, V and V. So once we are connecting the capacitors in parallel, then the potential across each capacitor remains the same. The charge is distributed in direct proportion to their capacitance. The capacitor that has got higher capacitance will have greater amount of charge. The capacitor that has lower capacitance will have a smaller amount of charge. So if Q charge was given by the battery, then the charges on each capacitor C1, C2 and C3 are respectively Q1, Q2 and Q3. So total charge Q is equal to Q1 plus Q2 plus Q3. Now Q1 is equal to C1V, Q2 equal to C2V Q3 equal to C3V, and the total charge Q is equal to equivalent capacitance C into V. We substitute these values of Q1, Q2, Q3 and Q. CV equal to C1V plus C2V plus C3V. V taken common on both the sides cancels out. The equivalent capacitance C is equal to C1 plus C2 plus C3. Now here C is equal to C1 plus C2 plus C3. Now if you remember this, here see, the equivalent capacitance is greater than the greatest capacitance of individual capacitor in the combination. Like for example, if we have again two capacitors of capacitance 2 and 3 microfarad and they are connected in parallel, then the equivalent capacitance will be equal to 2 plus 3 equal to 5 microfarad. That is greater than 3 microfarad. That is what the statement means, that the equivalent capacitance will be greater than the greatest capacitance of a capacitor used here. Okay, so today we have discussed series combination and parallel combination. It is the most important part of this lesson. Very often it is asked in the examinations. Next, we'll continue in the next video. Thank you.